Today, we're going to talk about the curious science that is the inclined plate settler. With this little gadget, I'm going to show you something that is seemingly nonsensical. If we take a look at this setup, you will see that there are two test tubes, mostly filled with water and a little bit of sand. And the way it's put together is I can have one be vertical and the other one be at an angle, or I can switch it and have this one be vertical and this one at an angle. So let's say I shake it up and get the particles all mixed up in the water. Then I hold it still. Which one do you think would settle first? Now one might think the vertical one, right? Because, well, gravity goes that way, and that's precisely the direction the particles want to go. But as I'm talking, you can see that that's actually not the case. The one in the slanted test tube is settling faster. It's settling so fast, actually, that, well, it's done. And the other one's not even close, even though gravity goes that way. So what exactly is happening here? First, we need to look at the science of settling. If you drop an object into a fluid, and its density is greater than the fluid, it'll most likely sink. How fast it'll sink is known as the settling velocity, which we normally note as v sub s. The settling velocity can be calculated by something called Stokes Law, which first states that how fast a particle will settle is determined by the difference in densities between the particle and the fluid it's in. So let's say a really dense particle, like a rock, is dropped in a non-dense fluid, let's say air, it's going to, well, drop like a rock. So the first part of the equation is to subtract the density of the particle from the fluid. Next comes viscosity, which is a fluid's resistance to flow. The more resistant it is, the more it's going to slow down that particle. So we divide by the viscosity. How fast a particle will settle, here on Earth anyway, is determined by gravity. So we multiply by the acceleration of gravity. The size of the object also plays a role in how fast it'll settle, so we multiply by the radius squared of the particle size. Finally, we multiply by a factor of 2/9 if we're using empirical units. That way our results come out in feet per second. And there you have Stokes' Law. So looking at it all together, it looks pretty complicated, but when you break it down into its pieces, it actually makes a lot of sense. So now that we know how fast a particle will settle, let's take a look at a particle settling in a test tube. A particle settling in the vertical tube has to settle all the way to the bottom before it hits a solid surface. In the case of our apparatus, the settling velocity is about 0.007 feet per second, and the water depth is about 2.5 inches. So the settling time for any given particle is around 30 seconds. Now, if the test tube is held at an angle instead, the distance that any particle has to settle to reach the solid surface is now only about 1/2 inch. So the time any particle takes to reach a solid surface is reduced to around 6 seconds. So our settling time has now been reduced from 30 seconds to 6 seconds. If you look at any engineering textbook, you'll likely see a diagram like this one, which pretty much says that if you reduce the distance a particle has to settle, then the settling time is reduced, which is what we just walked through. But that really doesn't tell the whole story, does it? Because the particles aren't just reaching the other side of the test tube. They're reaching the bottom of the test tube, and they're reaching the bottom of the test tube significantly faster in the slanted one than in the vertical one. So once they reach the other side of the test tube, what's causing them to speed up? If we take a close look at the test tubes, it becomes pretty apparent. The particles in either test tube float in a very similar manner. And given that all the factors in Stokes' Law for either test tube are the same, that would make sense. That is until the ones in the angled test tube start to gather against the side and reach critical mass. Once they group up, they really start to move. The reason for this is the same reason you see athletes in a lot of races group up, whether it's swimming, cycling, or even NASCAR. Any person, car, or in this case particle, that is by itself has to fight through all the fluid on its own. When the particles, or people, or cars group up, they begin to draft off one another. And once they begin to draft off one another, they really get to speed up. So by having one of the test tubes at an angle, the particles are going to do what they naturally would do, which is go that way because, well, that's the direction gravity goes. But they're not going to go that way very far until they hit a solid surface. Once they hit that surface, they start to group up. Once they start to group up, that's when they really start to move. And that's why we see the particles in the slanted test tube reaching the bottom faster than the horizontal one. In water treatment, when we want to settle out solids, we put all the water and solids into a big tank and pretty much just let gravity do what it does. And in traditional gravity settling, what we end up having is the vertical test tube. And the longer it takes the particles to settle, the bigger tanks we need. The bigger tanks we need, the more space is required, and the more cost. And what we've seen from our little experiment here is that if our clarifiers acted a little bit more like the slanted test tube than a vertical one, we could get away with significantly smaller clarifiers. How we do this in real life is through something called an inclined plate clarifier, where we take a bunch of inclined plates and we put them in our tank. And in between each one of these plates, it acts a lot like our slanted test tube here, where the particles go straight down, but they don't have to settle very far until they reach a surface. Once they reach that surface, they group up. Once they group up, they move to the bottom and settle out very fast. And we can greatly reduce cost and space requirements. What we see in real life is a reduction in volume by 80%, just by using the physics we see in our little experiment here. So a new facility can be 20% the size. Or we can put plates in an existing facility and greatly increase that facility's capacity. If you want to learn more about inclined plate settlers, there's a couple different places you can go. For municipal drinking water applications, check out murresearch.com. The address can be found in the video description below. For industrial applications, head on over to parkson.com and look at the Lamella. That address is also down in the video description. Thanks for your time today, and I really hope you enjoyed our little experiment.